So we'll again start a new lecture today, and what we'll do is that we'll first review the contents of last lecture, and then we'll end up we'll go on discussing this new lecture. So in the last lecture we finished our discussion on ferromagnetic materials with some thoughts on what was postulated as molecular field, which was later explained in terms of exchange interaction and exchange energy, which gives rise to magnetic ordering, whether it's whether in the form of ferromagnetic materials or in the form of antiferromagnetic ordering. So parallel or anti-parallel, but in both the cases exchange interaction is dominant. And then antiferromagnetic materials, of course, they have anti-parallel alignment of spins with equal and opposite spin magnitudes. So as a result, there is no magnetization, and this is found to occur in some metallic elements as well as in some oxides, where typically spins on one side are spin up and another kind of site are spin down. So for instance, in case of nickel oxide, if you look at 110 planes, the nickel atoms in 110 planes, one of the 110 parallel planes are spin up and the next 110 plane are spin down. As a result, they cancel completely and resulting in no magnetization. And then another variant of this antiferromagnetic ordering was ferromagnetic materials. Now there also you have this anti-parallel alignment of spins, but spins or magnetic moments of these spins are of unequal magnitude. So this is a very interesting scenario, and this is what we will discuss today as well, because this gives rise to a net magnetic moment, and this magnetic moment can be quite large, and as a result many times ferromagnetic materials come in the category of are explained in the just like they are ferromagnetic materials. And the materials which belong to this category typically are ferrites like iron ferrite, nickel ferrite, nickel iron ferrite, cobalt ferrite. So we look at those applications today, those examples today. And then we went on discussing a comparison of all these different kind of magnetic materials, and finally we looked at what is the power loss in a magnetic material with hysteresis curve. So today what we will do is that we will first have a look at the frequency dependence of magnetic permeability. So we said that just like you have in case of electric field, you have simultaneously sinusoidally varying AC electric field, you have a magnetic field which is also similar in the form H is equal to H naught exponential of I omega t. And this since now you know that if H is of this form, and you know that in a linear magnetic material B is equal to mu naught mu r into H. Now at high frequencies these two parameters B and H are related with some lag time. So if you write in the form of phasors, then B can be written in the form, if H is written in the form of H naught exponential I omega t, then B is written in the form of B naught exponential of I into omega t minus delta. So with this minus delta is suggestive of the fact that B lags to H by an angle delta. So this delta is nothing but your phase delay between B and H. So if you plot it on a real imaginary plot, then if this is your H, then B would be somewhere here. So this would be your delta. Okay. And so if you now, what is magnetic permeability? Magnetic which is mu is nothing but B divided by H, and if you now substitute the values, this is B naught exponential of I into omega t minus delta divided by H naught exponential I omega t. And if you just substitute rearrange the terms, what you get is B naught divided by H naught into exponential of minus I delta. And this term, being a complex quantity, suggests that mu is also a complex quantity. So as a result, magnetic permeability is a complex quantity. And this is similar to what we saw in dielectric materials, where we ended up establishing the same conclusion, and by taking the AC electric field. So this B can be simply written as B naught H naught into cos delta minus of B naught H naught I multiplied by B naught H naught sin delta, and this can be written as mu prime minus I mu double prime, and this is what. And similarly, loss tangent, and here mu prime is the real part of magnetic permeability, and mu double prime is the complex part of permeability. And similarly, just like the electric materials, you can define a loss tangent tan delta as mu double prime divided by mu prime, which is again representative of measure of loss in a magnetic material. Okay, so basically it tells you an idea about how much energy in the material is lost. So this is the complex dependence of magnetic permeability in the complex representation of magnetic permeability in a magnetic material. So now what we will do is that we'll get back to what is called as more pertinent topic, which is magnetic ceramics, and in this context what we are going to look at basically is ferrites. So these ferrites essentially, as the name itself suggests, these are iron containing materials. So we can have spinel, basically cubic structured ferrites. We can have hexagonal ferrites. We can have garnets. Garnets are essentially based on mineral form. So all these are strongly magnetic material. They are reasonably resistive in nature as well. As a result, they are used in applications where loss is an important thing. So you don't want to have high losses, you can use these materials. Moreover, some of these materials can have tunable Curie temperature. So as a result, you can change the composition of the material to change the Curie temperature and hence make it more useful for your application. And composition can also lead to changes in the magnetic characteristics as well, which is what makes these so tunability of magnetic behavior as well as Curie temperature makes these materials extremely useful for for variety of applications. And moreover, most of these are oxides and forms. Their stability, environmental stability is far better. There is nothing to oxidize further. So as a result, they are very useful materials. Now we'll go through each of these one by one with a little discussion. So first we will take up what is our spinel structured ferrites. And so essentially spinel structured ferrites are nothing but cubic packing of based on cubic packing of anions, and general formula by which they are determined is Ab2O4. So or rather you can now this formula Ab2O4 can be represented differently. Now to know about these spinel ferrites, we will go back to module 1 a little bit, because that is where we discussed these materials. So I'll take you to the slides of module 1, which are so this is something which we discussed in module 1. So a spinel structure is essentially spinel structured materials have formula of A2 plus B3 plus 2O4, or they are written as Ab2O4 or AO.B2O3. So you have essentially it's a mixture of two oxides, AO and B2O3. Now interestingly, the way cations arrange these themselves in various interstices defines whether you have an inverse spinel structure or normal spinel structure, and depending upon whether your structure is normal or spinel, the magnetic characteristics vary accordingly. So as a result, so essentially what you have is a FCC packing of anions, and here, since you have FCC packing of anions, you will have tetrahedral and octahedral site, and for per formula unit, for 4 oxygen atoms, you will have 4 octahedral and 8 tetrahedral sites, and the whole unit cell is made up by 8 formula units. So as a result, you have essentially 32 oxygen atoms, 8 into 4, so which means you have 32 octahedral sites in a unit cell and 64 tetrahedral sites. Now what happens is that in this material, in these materials, these sites are not completely occupied, as you can see, because cations are only 3 and interstices are 4 plus 8, 12 per formula unit. So as a result, there is a partial occupancy of these interstitial sites. So what you have is essentially 1/8 of tetrahedral and half of the octahedral sites are occupied. Okay, so per unit cell, out of 32 octahedral, only 16 are occupied, and only 8 of the tetrahedral out of 64 are occupied. So essentially the unit cell is like 8 FCC cells made by oxygen atoms in the configuration 2 by 2 by 2. So it's a 2 by 2 by 2 cube consisting of 32 oxygen atoms. And as I said, depending upon how cations occupy different interstices, the structure can either be normal or inverse. So essentially normal spinel has a formula which is A2 plus B3 plus twice O4, similar to that. Now what it means is that all the A atoms occupy tetrahedral sites, which means out of 4, since you have 8 formula units, you will have 8 A atoms. So these 8 A atoms will occupy all the 8 tetrahedral sites out of 64, and all the B atoms, which is 2 per formula unit or 16 per unit cell, occupy the half of the octahedral sites, which means 16 octahedral sites occupied. And you can do the bond balance, bond strength rule, as I told you earlier, to satisfy yourself with the stoichiometry. In case of inverse spinel, what you have is essentially a chemical formula is same, but conveniently for illustrating how these atoms occupy the interstitial sites, you can say that this half of the B atom, which means 1 out of 2 B atom, or in a formula unit, or 8 out of 16 in a unit cell, occupy the tetrahedral sites, and remaining B atoms and all the A atoms occupy the octahedral sites. So the examples of this structure are materials like Fe3O4. Most of the useful ferrites happen to be inverse in structure. So you have Fe3O4 or NiFe2O4, CuFe2O4, etc. And here, as I said earlier, half of the B ions occupy tetrahedral sites, and remaining half B ions and all the A ions occupy octahedral sites. So this is what is the spinel structure, and this is how it looks like. So you have this Ab2O3 spinel, and the red cubes are the so essentially, which one is the back? Yes. So essentially this is the kind of configuration you have. So this is the configuration of essentially one type of atom. This is the configuration of so you can go through the configuration yourself. So what you have here is the A atom at the tetrahedral side, and red one will be at the octahedral site. So structure is a little bit complex. I advise you to go through the books a little bit to understand the structure well. So let's go back to what we were discussing earlier. So what we were discussing earlier was this. So essentially what you have is Ab2O4 structure. So you can have normal, you can have inverse spinel. In case of normal spinel, you have which means 1/8 occupancy, and all the B atoms going to occupancy. And the example of normal spinel structures could be your zinc ferrite, magnesium aluminate, cobalt aluminate, etc. And inverse spinel so you have, so you can say AB2O4 as B dot AO dot O4. So B goes to tetrahedral sides, half of B, and half of B and all A go to octahedral sides. And the examples of such materials are Fe3O4, NiFe2O4, CoFe2O4, etc. Now, from the magnetism point of view, the spin of atoms going to tetrahedral site is opposite to that of those going to octahedral sites. Now, this is something which is ferromagnetic material itself. So, what you have essentially anti-ferromagnetic ordering, what you are going to have is a different picture. So, if this was true, then let us take example of Fe3O4. So, Fe3O4 can also be represented as FeO dot Fe2O3. It's a solid solution of essentially FeO and Fe2O3. And what happens here is you have two of, so your essentially you have your A ion is Fe2 plus and B ion is Fe3 plus. So, you have one Fe per formula unit going to tetrahedral site, and you have one, so we can write one Fe3 plus, one Fe3 plus and one Fe2 plus per formula unit going to octahedral site. So, if this was your octahedral site and this was your tetrahedral site, if I just make two columns, so what you have is per unit cell you have how many Fe ions going. So, you have octahedral site will have 8 of Fe3 plus and 8 of Fe2 plus ions, and this will have 8 of Fe3 plus ions. Okay. Now, what is configuration of Fe? Atomic number is 26. So, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, so that makes it 10, and then 3d6. So, depending upon whether you have Fe2 plus or Fe3 plus, so Fe2 plus according to Hund's rule will have 4 mu b of magnetization, because 1, 2, 3, 4, 5. So, for Fe2 plus all the S electrons will be taken off. So you need to rearrange D. So 5 of them go to 5 empty subshells, and then one goes here. So what you have here is 4 mu B, and Fe3 plus likewise will give you 5 mu V. 1, 2, 3, 4, 5. Because now you will take off 2 s electrons and 1 d electrons, left with 5 d electrons. So now doing the math, octahedral, tetrahedral, and we are going to calculate mu per unit cell. So we had 8 of Fe3 plus. Let's say octahedral side is spin up and tetrahedral side is spin down. So we are saying that they are opposite, to a spin up and a spin down. You can take it the way you want it, but essentially it's going to give rise to net magnetic moment. So if 8 Fe3 plus will give rise to 40 mu B, and 8 Fe2 plus will give rise to 32 mu B, and here 8 Fe3 plus will give rise to 40 mu B. So essentially what you will have is net will be, so mu net per unit cell will be equal to 40 plus 32 mu B minus 40 mu B. So this 40 cancel each other. What you will have is 32 mu B per unit cell. And if you want to calculate mu net per formula unit, it will be 4 Bohr magneton per formula unit, which is a very large magnetization considering magnetic materials into account. This is essentially the way you work out magnetic moments for a ferrite material, and it's a very simple way of doing it. Remember that the spins of octahedral and tetrahedral are opposite to each other. They may or may not be equal, but they are opposite to each other. So as a result, they give rise to net magnetization. Now similarly you can work it out for other ferrite materials like nickel ferrite, cobalt ferrite, etc. They are again simple. You just need to work out what is the net magnetic moment of each ion by applying Hund's rule, and take the oxidation state, and then work out what is the final magnetic moment of that material. Another thing that you can do with spinels is, with the spinels you can also make mixed spinels. And this mixed spinels is nothing but, if you have one type of compound, let's say A prime, B prime, 2O4. So let's say X of this, then you can make another 1 minus X, A double prime, V double prime, 2O4. So this is nothing but mixed spinel is nothing but solution of two different kind of spinels. So where A prime and A double prime substitute for each other, and assuming that there is a random occupancy on the designated sites, and then B double prime and B prime again occupy for each other. So as a result you have mixed occupancy of the intersites. So for instance you can take NiFe2O4 and ZnFe2O4. So let's say this is 0.6 NiFe2O4, and you can make it 0.4 NiFe2O4. So here now what you need to do is that you need to do the same exercise. So go to octahedral, tetrahedral sites. Now you know that nickel ferrite is inverse, zinc ferrite is normal. Make sure you get the site distribution, the distribution of ions in the sites correctly. Work out the magnetic moment. So you take this spin up, spin down, work out the magnetic moment, multiply this by X and 1 minus X for the relevant ion, and then get the final moment per unit cell or per formula unit. So you can do it the same way, it's just that it's nothing but rule of mixtures. So so it's a simple exercise. I'll leave it to you to do it as a homework. Essentially, what I'm going to ask you is calculate the net magnetic moment of a mixed spinel compound, which is Ni Fe2O4 Zn Fe2O4 1 minus x, where x work out mu net versus x up to x for x up to 40 mole percent. So this you can do it at home. Okay. Another thing that you find in spinel perovskite, cubic spinel ferrites is that they have low magnetic anisotropy, which means they don't have a strong dependence of magnetization on the crystallography. So on the crystallographic direction. So as a result, they are magnetically soft magnetic materials. So they don't have large hysteresis losses, and some of the exceptions could be cobalt containing ferrites, which tend to have large somewhat large magnetic anisotropy, and they also have very large coercive field strength. So they could be exception. So but otherwise, by and large, these magnetic ferrites have low magnetic anisotropy, which makes them useful in the polycrystalline form, and as a result, the switching is easier, and that is why they are called as soft magnetic materials with low coercivity, and they also so just like a ferromagnet, ferrimagnetic, these ferrites also show a hysteresis loop just like a ferromagnet, and they also tend to have reasonably large Curie temperature. I'll show you a table where Curie temperature etc. for these ferrites are given. Typically, if you look at ferrites, they might have Curie temperatures above the room temperature, and which are composition dependent as well. So, you can say magnetization and Tc are composition dependent and tunable. Okay, so you can tune the properties by changing the composition. Another category of magnetic ferrites is hexagonal ferrites. So as the name itself suggests, these are hexagonal structured, and the parent structure for these compounds is basically magnetoplumbite, which is hexagonal compound, and typically you call these materials, they are also called in literature as M-type ferrites. M-type comes from magnetoplumbite, so M-type ferrites, and the model compound, the material which is used to represent the structure is typically barium ferrite, BaFe12O19, very long formula unit, and so this is barium ferrite. Hexagonal in structure, consists of 19 oxygen atoms, 12 iron atoms and 1 of barium atoms, total of 19, 12, 31, 32 atoms per unit cell, and the structure and the unit cell has 64 atoms or 2 formula units. So, which means the structure will have 2 of barium atoms, 24 of iron atoms and 38 of oxygen atoms. Essentially, you can easily represent this structure as if it's a mixture of it's a mix of CCP and HCP packing, and these are close packed layers which are made by barium and oxygen ions, and this can happen because CCP and HCP structure, you know that you have, this is your HCP, AB, AB, and then in between you can have ABC, ABC as well. So, this is ABC, ABC. So, all you need is a stacking fault essentially. So, that is where you have a stacking fault. So, a mix of CCP and HCP layers giving rise to a total of eventually giving rise to a hexagonal structure, and material is bound to have stacking faults. So, essentially stacking of CCP HCP layers with some stacking faults in between, and the base structure is formed by barium and oxygen ions, and iron atoms occupies the interstices. So, and so iron atoms here, they occupied interstices of the type octahedral. So, they occupy both octahedral, tetrahedral, and another peculiarity of this structure is that one of the iron atoms remain, one Fe atom remains 5-fold in coordination. So, this is one peculiar thing about the structure. So, not only you have octahedral and tetrahedral coordination, but you also have a 5-fold coordination at certain places in the structure. The way you can change the magnetization of this magnetic behavior of this material is, so you have Ba Fe12O19. So, naturally if you substitute iron by some other atom, you will change the net magnetic moment. I will show you in a while how these magnetic moments are distributed in the lattice, but it's quite straight exercise to work it out. When you replace iron, let us say, by aluminum, you will change the magnetic characteristics. You can also change barium by strontium. Barium is a non-magnetic ion, but you can change barium by strontium, so it changes the strain environment of the material. So, basically size and valence being different gives rise to changes in, so not only so you have changes in the size and the valence, and they give rise to changes in the magnetic behavior of the material. So, coming back to magnetic characteristic now, you have 9 iron atoms going to octahedral sites out of 12, and 2 iron atoms going to tetrahedral sites, and 1 iron atom remain 5-fold coordination. So, this makes up 12 Fe, and the formula is Ba Fe12O19. So, essentially it is going to be BaO dot Fe2O3 into 6. So, this is how the structure is essentially, and now you can also see why it is like a mixing of hexagonal and cubic layers, because Fe2O3 has a hexagonal structure, as we have seen from the module, as you can see in the module 1, which is based on Al2O3 type structure, and then BaO will have rock salt structure, and if you mix these rock salt and hexagonal structures, you result in this Fe12O19 kind of structures. Of course, there are going to be more number of layers containing Fe2O3 than BaO. So, this is the structure. Now, here you can see that Fe2 plus, Fe is in Fe3 plus form. So, Fe3 plus form means magnetic moment per atom is going to be 5 mu b. So, you have 5 mu b of this thing. So, based on that, if you rearrange them in the various sides, so you have 9. So, you have octahedral, tetrahedral and 5-fold. Now, here what happens is that in case of octahedral sites, out of 9, 7 Fe are spin up and 2 Fe are spin down. Now, up and down you can of course choose, but if you choose one up, you have to choose other one down. And with reference to this, the 2 in octahedral down sites, they are spin down, and 1 in 5-fold so 1 in 5-fold is spin up. So, essentially what you have, total of 8 iron atoms spin up and 4 iron atoms spin down. So, basically per formula unit 8 Fe spin up and 4 Fe spin down. So, mu net would be 8 into 5 mu b spin up minus 8 into 4 into 5 mu b spin down, and what this gives rise to is essentially 20 mu b per formula unit. So, essentially what you have is 20 Bohr magneton of magnetic moment per formula unit of barium ferrite. Now, for per unit cell, if you want to calculate, then per unit cell mu net is going to be equal to 2 multiplied by mu net per formula unit, and this would be 40 Bohr magneton, and this is a very large magnetic moment for a material, and that is why this makes barium ferrite a very useful material. Another features of this material, this has high magnetic anisotropy, which is expected for a hexagonal material, and it magnetizes easily along 0001 or C axis of unit cell. So, C axis being the easy magnetization direction of this material. As a result, this material is now, since it has very large magnetic anisotropy, it happens to have high coercivity, and this coercivity can be anywhere between 50 to 100,000 kilo ohm kilo ampere, 50 to 100, sorry, not 1000, 50 to 100 kilo ampere per meter, and this depends upon microstructure and composition, etc. So, as a result, this material is characterized as hard ferrite. So, essentially barium ferrite is a hexagonal material with large number of atoms, two formula units per unit cell, making up the hexagonal unit cell, which is essentially based upon iron oxide structure, Fe2O3 structure, hexagonal iron oxide structure, and this contains ions in such a position that it gives you a very large magnetic moment per unit cell of the order of 40 Bohr magneton. So, this is a large number. Now, what we are going to next take up is essentially the case of garnets. Now, these garnets are essentially known as minerals. So, basically the general so essentially when you talk about garnets, you are talking about minerals, but from the point of view of magnetism, the general formula for garnets on which they are based upon is essentially they are YFeO compounds, yttrium iron oxygen compounds, and the general formula for them is Y3Fe5O12. So, this is the general formula for the compounds, and a more general formula if you, so yttrium is a rare earth ion, so you can make it R3 Fe5O12. So R could be Re, let's say, so Re3 Fe5O12, which is a Re is a rare earth ion. So essentially you have here two magnetic ions, this is magnetic and this is magnetic, both of these are magnetic ions. So the fact that you have two kinds of magnetic ions, one is the rare earth, second is the iron, the total magnetic moment of this material is quite modifiable, tunable by putting in different kind of elements in there, and as a result you can play around with this material. Now, so this example of this Re3, Re can be, you of course you can of course have yttrium, you can have lanthanum, you can have samarium, you can have gadolinium, neodymium, any kind of rare earth atom can be used here to tune the magnetic moment of this material. And this material again is a quite complex from structure wise. So you have Y3 Fe5O12, the structure is cubic and the structure contains 8 formula units. So 8 formula units multiplied by one of this. So 8 formula units of Y3 Fe5O12 make a cubic structure. So this is a very large compound. So total of, you can calculate 12 plus 5 17 into 3 20 plus 3 20. So that means 160 atoms per unit cell, and this gives rise to very large a large structure which is a highly tunable magnetic structure. Now here since iron is a 3D ion, iron's contribution mainly comes from spin magnetic moment, because in iron the orbital magnetic moments are quenched because of crystal field, as we discussed earlier in the form of in the case of paramagnetism. So the only magnetic contribution to iron comes from spin magnetic moment. So as a result Fe3 plus will have 3 mu b, 5 mu b, sorry. In case of these rare earth ions or lanthanides, you can say they have both, they are 4f kind of atoms. So as again, if you recall the discussion on paramagnetism, they have both orbital and spin contributions. As a result, the magnetic moment of these is quite different from those of iron. So it depends upon the strength of magnetism in these ions, which is a crucial factor in governing the type of magnetism that you get out of these compounds. So what you have in this structure essentially is, so here R atoms, Re atoms here, Re atoms are cubic coordinated, so which means they have 12-fold coordination. Now out of 5, so 3 Re atoms are cubic coordinated so essentially, let me just put it this way, in one unit cell. So you have, since you have 8 formula units, so 24 Re atoms are cubic coordinated, and you have 8 into 2 is equal to 16 iron atoms octahedrally coordinated, and 8 into 1 8 iron atoms as tetrahedral coordination. So now here, so basically 24 Re atoms, you have, sorry, now here you have essentially 8 into 3. So this should be 24 Fe atoms, because the structure, because the formula is Re3 Fe5O12. So as a result, you have 2 iron sitting on octahedral sides and remaining 3 go on the tetrahedral. So 24 iron atoms on tetrahedral side. So please note that modification. So you have 24 Re atoms going on 12-fold coordination. You have 16 iron atoms which are octahedral coordination, and you have 24 iron atoms which are tetrahedral coordination. And if these 12-fold coordinated material atoms were spin up, they will give rise to some magnetic moment, and this magnetic moment would be 24 into mu r. Mu r is the strength of magnetism in the lanthanide ion, and this could be anything from 0 to any number higher onwards. So mu r is the strength of moment of r ion multiplied by mu b, and octahedral side you have spin down, spin up again, and this would be your 16 into 5 mu b, and this would be down. The tetrahedral is the one which is down, so this is 24 into 5 mu b. So net magnetization, so net magnetic moment to be precise, is equal to 24 mu r plus 8t minus 120. So I can take, of course, 3 out of it. I can take 8 definitely out of it, because 8 will mean it's a 8 formula unit. So it would be 8 multiplied by 5 minus 3 mu r, or sorry, so you can say essentially this is minus 5 plus 3 mu r into mu b, and of course you take the mod to get the magnetization. So essentially you can take spin down, spin up, and spin down the way you want it, but the fact is one is a spin up, then another one will be, the opposite spin will be spin down, or vice versa. So essentially you can say the net magnetic moment is per formula unit would be, so we have calculated what is the magnetic moment per, this is per unit cell. So 8 unit cells multiplied by 3 mu r minus 5 into mu b will be the magnetic moment. So per formula unit would be divided by 8. So what you will have essentially is 3 mu r minus 5 into mu b will be the net magnetic moment of a garnet per formula unit, and when you take the magnetic moment, finally you take the mod of it. So positive or negative, depending upon how you calculate, the sign will cancel each other, and this mu r will be 7 for gadolinium and it's 0 for yttrium. So depending upon which ion you choose, you can tune the magnetization of this material, and the magnetic moment will be dominated by rare earth ions if, of course, you can see from that, if mu r is greater than 5 by 3. If mu r is greater than 5 by 3, then dominated by Re ions, otherwise it is dominated by iron ions. So this is how you work out the magnetic moment of garnet. Another thing which is possible to do in garnets is both Tc and mu net can be tunable by tuning the composition, and this is basically because of coupling between the rare earth ions and the iron ions. Typically as temperature increases, the mu net decreases. So as a result, for strongly magnetic ions like gadolinium or terbium or diphtherium, that is where, and this is especially true for these ions, basically when you have these ions present in the system. in this context, the gadolinium doped composition, which is GD 1.8 Y 1.2 into iron 5 and oxygen 12, has a rather stable magnetic moment, and and it has a temperature window of the operation of 50 degrees centigrade. So, in this case, in garnets, the temperature window of temperatures can be quite unstable. So, as a result, you need to choose the composition which give you a rather stable window of operation, and this is okay for garnet. Garnets are very useful for microwave applications because they have high resistivity. So, as a result, they have low losses, and they can be very useful for microwave frequencies. More importantly, garnet can be prepared quite easily in the single crystalline and polycrystalline form. So, as a result, fabrication is easier, and it's very easy to tune the magnetic as well as structural characteristics of this material by changing the composition. So, these are the three different kind of ferrites that we have discussed today. We have discussed the iron containing, or basically spinel structured cubic ferrites, which are essentially most of them being iron containing inverse spinels, and they have very large magnetization, and they also tend to have very large Curie temperatures, which we'll see in the coming lecture. And then you have what is called as a hexagonal barium ferrite, which has very large magnetic moment, but it has very large magnetic anisotropy, unlike cubic spinel ferrite. Cubic spinel ferrites are not anisotropic, and that is why soft ferrites. Whereas barium ferrites, they have large magnetic anisotropy, and they tend to be hard ferrites. So, they are used in applications where large coercivity is required. Similar, and then we had garnets, where it's a mixture of rare earth and iron containing material. As a result, you have very large window of structure and magnetic tuning of the material, and they typically are used for microwave applications where losses are of great concern. So, we will finish today's lecture here. In the next lecture, we will complete some of the remaining characteristics of these three different kind of ferrites, look at the properties, and then finally we focus upon the applications in the next class. Thank you.